Welcome to part 2 of the bus protection. My name is Pratap Mysore. In the part 1, we introduced the concepts of the bus protection. We talked about various bus arrangements, and then we also talked about the CT polarity and zones of protection. And we mentioned that under normal conditions, the current, sum of all the currents may not be zero on the secondary side of the CT connection in a bus protection, even though the primary side, some of them should be equal to zero. This is due to CT saturation. That could be due to the offsets, DC offsets in the currents, and also the inaccuracies produces some operating current. And we also talked about the phenomena how the CT saturation. We said that the CT will never saturate at time t equals 0, and then even if it saturates, it comes out of saturation after a certain amount of time. We make use of these two to make a bus protection a very reliable and a secure device. The one way we can do is if you are monitoring the currents coming into the relay and coming into the bus and going out of the bus by connecting all the CT secondary sides in parallel and connecting the relay in a differential manner. Suppose if the CT is saturating, what we do is we put a time delay on the relay, so even if it sees a differential current, it does not operate for certain amount of time. It could be 6 cycles or 10 cycles or whatever time it takes for the CT to come out of saturation. Once the CT comes out of saturation, there will not be any differential current for an external fault. So you can delay the operation of the relay to allow the CT to go into saturation and come out of saturation. The problem here is if there is an internal fault, this relay will take the same amount of time. If the relay takes a lot of time to operate, that means you are delaying clearing a high fault current, which is normally seen at buses. So which could not be a great idea, but this has been used by several utilities by connecting a simple inverse time overcurrent relay, and then for an internal fault you see very high currents, so your operating time will be much less than for a fault outside where it is only the differential current that is operating. Okay. The second method we talked about was that we assume that CT is saturating under external fault conditions, and then we look at the impedance of the CT, which is mostly resistive, and then we looked at the total impedance of the loop from the relay location up to the CT, which is saturated, and then then you select a stabilizing resistors to push most of the current through the saturated CT and then prevent relay operation by setting the pickup milliamperes to much higher value. Most of these relays are calibrated in voltage, so the high impedance relay, this is called high impedance because we are converting a small low impedance relay which was 0.04 ohms as I show in the previous examples, by putting a 500 ohm resistor and making it a higher impedance relay. So if you look at, this is called a high impedance relay. Today we will talk about this and also the other types of relays which are used for bus protection. A high impedance relay, here if you look at it, you assume the CT saturates and then you calculate the voltage seen by the relay for when the current flows through the cable and the faulted and the saturated CT. So if I look at it, I can write it as an equation: VR equals I fault times 2 times R cable, because you have a let me see here, this is my cursor. I have a cable connected from the relay location up to the breaker location, and you have a return cable coming back. That is the total length of the cable. That's why we multiply that as 2 times the resistance from the relay up to the breaker, of the cable up to the breaker, plus RCT, and then the fault current. The relay is set in such a way that it operates if the VR is greater than the V setting. Okay, so you can always look at the maximum voltage drop that is seen at the relay location, assuming a full CT saturation, for the farthest CT in the switch yard, and calculate or in a breaker which is seeing the maximum amount of CT, calculate the maximum voltage that could be seen by the relay, and then set this relay with a margin. It could be 2 times or 1.5 times depending on manufacturer suggested settings. So once you set the relay will never operate for external faults. But if there is an internal fault, then most of the current is pushed through the relay, which has got a very high impedance. It develops a very high voltage across that. So, and then the relay will operate as soon as the voltage exceeds the setting. So the effect of stabilizing resistor, if you look at it, it reduces the spill current through the relay coil. Relay is set about the maximum voltage drop across the cable and the saturated resistance. It's a very simple calculation. You have a layout of the substation. You know where the CTs are connected. Then you just calculate for your fault currents seen going through the CT for a fault just outside the zone of protection, just close to the substation, but outside the zone of protection. And then you know the impedance. You multiply that by the fault current. You calculate the maximum voltage that is seen in the relay, and then you set the relay. Here, you have got an external fault current of 20,000 amps. Got a CT ratio of 2000 to 5. Then secondary current is 50 amperes. It is just the ratio of that. And then CT resistance 0.002 ohms per turn, which I am using it as a typical value. Please check with the CT data sheet that will provide you with the resistance value. And here it is 400 turns, so you get 0.8 ohms. Cable length is 1000 feet or cable, and then it's typically if you use the number 10 AWG wire, that is American wire gauge, it has got a resistance of 1 ohm per 1000 feet. So from the relay point up to the breaker location is 1000 feet, and then the current comes back through a second wire and the cable, and that is another 1000 feet. So we get 2 ohms plus 0.8 ohms is a CT resistance, and then the voltage that is developed for a fault outside this particular location of the CT is 140 volts. The relay is set to 140 volts. We generally do not set it at the same value. We set with a margin, it could be as high as 2 times this value. Okay, and as you know, for an internal fault, it always develops a voltage which is much higher than that, because the current CT is trying to push current through this high impedance. What are the requirements of this? All the CT ratios are equal. This is just a general statement here. We'll look at this. You can use multiple CTs, but there are various arrangements where you can connect the relay across the full turn, and you can use the tap ratio also. For this, there are manufacturers' bulletins and application notes. Please do refer to that. We are looking at the basic concepts here, and if you want to really apply, you have to go through those to see how to use this if there are CTs with the different CT ratios. Okay, all CTs can develop the voltage required to push the current through the shorted CT. What it is if there is a fault outside this zone of protection, then you get voltage. You get a voltage that is developed across the relay, but the same voltage is seen by all the CTs for this fault. And then the way it is connected is you want to keep the cable impedances low, so that your settings are is in a manner within the range of the relay. So you parallel all the CTs in the switchyard through a junction box, and then use a cable from there to connect it to the relay. Relay is a high impedance relay. As I mentioned to you, it is just like a voltmeter. You are using 2 probes to go back and measure the voltage at this junction point. So what would be the current going through this to the relay? As I mentioned, it is a higher impedance. It is only in milliamperes. Most of the currents are exchanged between the CT secondary side through the number 10 gauge wire or higher gauge wire, whatever that is used in the switchyard. And we make junction boxes there and then bring the relay. I have shown you here only one phase. In case of 3 phases, you will have 3 CTs which are connected in Y. The common point where neutral will be here, and there is a common point. You have got an A phase, and you have a B phase and a C phase, and the relays are connected like that. Okay, this is how the 3-phase CTs are connected. There should be only one ground in the CT connection, regardless of number of sources. Otherwise, you might bypass some of the currents that is going through the relay. How do we set this relay? Determine the maximum three-phase and single-line to ground fault currents for faults outside the zone for each of these circuits, as I mentioned earlier, and then measure and compute the cable resistance from the junction box up to the CT, and calculate the voltage VR for three-phase fault and single-line to ground fault. The difference between single-line to ground fault and three-phase fault is, in a three-phase fault, the current goes only through one phase of the cable. There is no current returning to the relay because sum of all the currents at the junction will be equal to 0. Okay, and select the VR settings, that is whatever that is applicable. And then, as I mentioned, when there is a fault, it develops a voltage high enough across the relay, and if your setting is set to twice that amount, for example, in this case we selected a V140 and then we set that to 280 volts. Now we talked about in instrument transformers, we talked about the C ratings. Normally for a high impedance relay, we try to use the highest C rating factor to allow the CT to develop the voltage that is required for the relay operation, even for internal faults. Well, here we have taken C800. The knee point also we defined the point at which you draw a line on the excitation characteristic. It's at 45 degrees. Or in case of Europe, they take 10% increase in excitation voltage results in 50% increase in current. That is defined as the knee point. On a C800, it is around 430 volts, and the voltage in the relay cannot exceed exactly 900 volts for C800, and the practical value of the setting should not exceed 67% of 900 volts, 603 volts. So you should not put extremely long cables and then develop it, and then if you come up with a setting which is higher than this, there is a likelihood that the CT saturates even for internal faults, and then most of the currents goes through the in magnetizing these cores at these higher voltages. Okay, and the typical relay impedance is about 2000 ohms, and this can be as high as 5000 ohms. Total fault current might be as high as 200 amps. The voltage the relay pickup and also CT voltage developed across the relay exceeds the relay pickup voltage and also the CT voltage rating. So now, if you have, for an internal fault, it develops such a high voltage because suppose if you have 2000 ohms and then you're pushing about 200 amps, and that would be about 400,000 volts, right? Which is very high. It won't develop that much because the CT saturates and develops it. You get very high peaks of voltage. In order to protect the circuit, what we do is we put a voltage arrestor, surge arrestor equivalent across the relay coil, across the CTs, to prevent any damages. And it's called a thyristor or a thyroid or MOV, and this is how we connect it across, so that if the voltage goes very high, then it limits the voltage and bypasses most of the current through this nonlinear resistor. And you put a high element or a simple overcurrent element here. If the voltage is too high, then the current goes through this, and this is the IH will operate under such conditions. Okay, this is just to prevent damages due to very high voltages developed for an internal fault. As you see here, that the basic requirement of these is the CTs that are used for high impedance protection should be able to develop, must be capable of developing voltages required for the operation of the relay. And second thing is, most of the CT ratios are generally the same, so that you can connect them in parallel, so the differential current will be equal to 0. If you have different CT ratios, if they connect in parallel, you might have issues. But if you have CTs with different CT ratios available, then you have to use the same CT ratio for to make them for a parallel connection, and then connect the relay to the full winding of the CT. This is explained in several application notes of the relay manufacturers. For those who are trying to go and set the relay, please do refer to those for such special applications. The second requirement here is you try to use the maximum full rating of the full rating of the CT by connecting it to the full winding, not the tapped. As I mentioned in the instrument transformers, CTs will have 5 taps as per ANSI standards in the United States. Yeah, we have to look at other standards in different parts of the world to see what are the minimum, how many taps are available in that, in the CT. The reason why we use full tap is we want to use the full capability of the CT. If it is C800 at 2005, you try to use 2005 so that you can get C800 capability. If you use the tap CT tap of 1000 to 5, then your C800 becomes C400, as we discussed in the instrument transformers. So the sensitivity of the relay also, we can select it here. IR is VR divided by ZR. Excitation currents of all CTs that we have to make sure you check the excitation current from the excitation curves of the CTs at the voltage that is developed, and then you can calculate what is the minimum fault current that is required for the relay to operate. I'm presenting you with all the facts that are used in determining the settings, in determining the minimum pickup and others. Please go through these slides again. You can replay them because it is a recorded one. Then you can go back and try to digest most of this. So that this, I'm trying to put these information so that for those who are doing the settings can look at these numbers. There are references here. I have given most of these are United States manufacturers. Then ABB is there, and these are very nice components. If these links are not, they have changed over the course of time, please go back to the geindustrial.com or digitalenergy.com. I think now they have changed the name. And then you have got a ABB, or you have got Basler Electric or Schweitzer Electric. These are US manufacturers. You can look at it. If you have regional manufacturers like Siemens in Europe, you can use this Europe. They will have application loads. Please do go through that for the high impedance. Now, the advantage of the high impedance is they are easy to set. All CTs are parallel in the switchyard, reducing the cable lengths. CTs with same ratio or similar characteristics are desired. Then if you have multiple CT ratios, you have application notes, you can look through that. Sensitivity reduces with many CTs in parallel. This is in the high impedance, and with a lengthy cable runs, also your voltage developed is higher. That means for an internal fault, if you develop that much amount of voltage, some of that voltage is the currents get diverted in magnetizing the CT codes at higher voltages. At higher voltages, you will have higher magnetizing currents, so the current through the relay is decreased by that amount. It may not be possible to set the relay in a system with lower CT ratio than high fault currents. It is sometimes difficult. It is difficult to use this scheme where zone switching is required. When do we said we have zone switching? Suppose if you have a transfer break, I should not take that as a transfer breaker. If the breaker has a problem, you have to connect some other breaker and switch the CTs from this main breaker to other breaker, then it becomes a little bit difficult. There are always solutions available to this. Please refer to the manufacturer's application notes for those who are pursuing your career or continuing as protection engineers in utilities or in the power industry. The other option for us is to use what are called restraint windings. We talked about delaying the operation of the relay to come out of saturation. We talked about putting resistance in series with the relay coil, making it a high impedance relay, and then prevent relay operation for CT saturation for external faults. And this is the third method. Instead of using stabilizing resistors, we are using restraining winding. So each CT input to the relay, they are not connected in parallel, that is disconnected, and then you bring each CT connection into the relay, and then they have what are called restraint windings. The current is monitored through each of these restraint winding, and they are all summed vectorially inside to create an operating current. It is I1 plus I2 plus I3 plus I4 that forms the operating current in the relay. So the criteria here is you look at the total current in each of these windings, and then you set your pickup, the operating pickup of the relay based on the ratio of the operating current to the amount of current that is flowing in each of these restraining windings. So the other names for this is bias differential or percentage bias differential. And then the other important thing is this relay is still a low burden impedance. Like what we mentioned in the earlier slides, these are just 0.04 ohms, and then but they do have restraining element. So now, instead of giving a fixed setting, the pickup of the relay depends on the ratio of the operating to the restraining current. Operate current is the vectorial sum of all the currents coming into the relay. Restraining current is just a magnitude of all the currents which are added here. So it is, you can look at it, IR is K times IR1 plus IR2 plus IR3 IR square. It is a scalar addition of all the currents in each of these restrained winding. So if they are all in phase, then your operating current will be equal to IR1 plus IR2 plus IR3 plus IR4. If two currents are opposite to each other, like in the example we took earlier, IR1 and IR2, which is coming from breaker 1 and 2, were coming into the bus, 3 and 4 were going out of the bus. So IR1 plus IR2 and IR3 and IR4 vectorial sum will add up to 0. So there is no operating current, but the restraining current will still be there because they are scalar sum of all of them. And K is a factor depending on the relay type. It is either 1 or it is 0.5. Sometimes they take the average, they just sum all the currents and divide it by 2 and then call it a restrained current. And so a few other manufacturers just use 1, they just add all those things. There are other manufacturers who take the maximum of the currents. If IR1 is the maximum current input into the relay, then the restraining current is set as IR1. Okay, this is another relay manufacturer type. So your restraint current, the way it is defined, is different and varies from manufacturer to manufacturer, but the operating current remains the same. The slope is defined as I operate to I restrain, and the relay operates if the I operating current is greater than the slope, then slope times I restrain divided by 100. Slope is a percentage slope. That's why we have got that 100. So if the current, if the restraining, let's take an example. If the operating current is 1 ampere, and then if the restraining current is 2 amperes, if the slope is set to 50%, 1 divided by 2 is 50%. It is a threshold of operation. Suppose if the operating current is just 0.5 amperes, and if the restraining current is 2 amperes, then 0.5 divided by 2 is 20%. And if the slope is set to 50%, the operating current is less than slope times 20% of the restraining current. So the relay is 50% of the restraining current. If the slope is set to 50, then the relay does not operate or restrains from operation. Okay. So we can define a characteristics. We set a minimum operating current that accounts for all the inaccuracies of the CTs, and then as the restraint current increases, then we increase the pickup of the relay based on the amount of the restraining current, and the slope is just the ratio of the operating current to the restraining current. Then you have a high set. If there is a very high internal fault, if the current is too high, then you don't even bother to check what is the ratio of the operating current to the restraining current. If it hits a high value, you operate right away at a high set. So you have another relay here which has got two slopes, S1 and S2, and if the current is low, you have a minimum operating value. If the current is low, it is going at 25% of the restraining current as a threshold of operation. If the current is high, you increase the slope to 50%, so it needs higher operating current to operate at higher restraint current. When do we need this kind of a characteristics? If the current is extremely high, the inaccuracy of the CT, the current, the inaccuracy is also increased with the increase in the current. So here at low currents you have a lower slope, at higher currents you have higher slope to account for higher inaccuracies. There are another manufacturer who gives you different types. The advantage of the microprocessor based relay is that you can shape the characteristic to whatever you think would suit and you would provide. Okay. Definition of the restraint current depends on the type of the relay, as I told you. If I have two inputs, I1 plus I2, one relay manufacturer one puts it as I1 plus I2 by 2. The second one says I1 plus I2. The third one says maximum from I1 and I2, which we discussed before. The low impedance protection schemes employ external fault detection techniques to detect your saturation, CT saturation. What happens, as I mentioned earlier, at the time t equals 0 when the fault occurs, CT never saturates. So if it is an external fault, sum of all the currents must be equal to 0, but there is a sudden change in the restraint current. It was just seeing the load current, now it sees the fault current, the restraint current value increases. There is a sudden change in restraint current, but there is no operating current still, as if it was a normal operating condition. So the relay says that there is a sudden change in current, restraint current, and there is no change in operating current. And then it waits for certain samples, 2 samples or 2 milliseconds, depending on the type of the relay, and says, this is an external fault. But after 1 or 2 milliseconds, the CT saturates. If it saturates, then you start seeing the operating current. So as soon as it detects that the fault is external with no operating current but high restraining current, the relay either blocks or it changes the slope from 25% or whatever you are setting it to a very high value up to 90%, depending on the type of the relay. So it restrains the relay from operating by increasing the slope, by increasing the pickup of the relay as soon as it detects that it is an external fault. These are widely used in modern relays. So if you have this as an operating, it's a lot easier. If it is an internal fault, then you see operating current and restraining current at the same time. It goes from one point to another. If it is an external fault, you suddenly see an increase in restraint current, but there is no increase in operate current. And then as the CT starts saturating it, you start seeing the operating current. So this is how the relay can differentiate whether the fault is internal or external, and then make it more sensitive by reducing the slope for internal faults and changing the slope for external faults. So this we covered. In addition to this, some of these manufacturer relays use directional comparison. It just looks at the direction of all the currents. If the fault is on the bus, the currents will be flowing towards the bus. If the fault is outside, at least one current is outside, 180 degrees out of phase with the rest of the currents. And you can use this for determining whether the fault is internal or external. This is also used in several relays. The great advantage of the low impedance relay is that you can use different CT ratios, and then in a microprocessor based relay you can tell that the CT input 1 is 605, CT input 2 is 1205, or CT input 3 is 2005, and then it automatically corrects the magnitudes of the currents to calculate the operating restraint current. Okay. And also it has an element, if you get a very small amount of operating current well below your minimum pickup, then it says that there is some CT connection problem. So your open CT circuit detection is also available in this. Other advantage of this are you have fault recording, metering, and other protections such as overcurrent and breaker failure protection, which could be part of the your microprocessor based relay. There is Protection and Control magazine, which is published by Alex Apostolov. It is an excellent resource for all the protection engineers or those students or engineers who are pursuing a protection career. They cover the classical aspects of relaying and also give you the latest technology and trends in protection industry. It's a good place for you to go back and then refer to this to find out. And then the references are given here. That on these are different places you can go back and then read through and